Imagine walking through a city you've never visited before. No map, no street signs, no asking anyone for directions. You take out your phone, open Google Maps, and somehow your phone knows exactly where you are. Not just the city, not just the street. Sometimes it can locate you within just a few meters. But here's the strange part. Your phone isn't looking down at you from space. And it isn't simply asking a satellite, "Where am I?" So how does it actually work? How can tiny satellites flying thousands of kilometers above Earth help your phone determine your exact location? The answer involves radio signals, incredibly precise atomic clocks, mathematics, and even Einstein's theory of relativity. This is the story of how GPS knows where you are. GPS stands for Global Positioning System. It's a satellite-based navigation system originally developed by the United States. Today, GPS is part of a much larger family of satellite navigation systems known as GNSS. There are also systems such as Europe's Galileo, Russia's GLONASS, and China's Beidou. But when most people say GPS, they're usually talking about satellite positioning in general. The basic idea is surprisingly simple. There are dozens of navigation satellites orbiting Earth. These satellites continuously broadcast radio signals. Those signals contain extremely precise information about the satellite's position and the exact time the signal was transmitted. Your phone receives those signals. Then it calculates how long each signal took to travel from the satellite to your phone. Because radio signals travel at the speed of light, your phone can use that travel time to estimate the distance to each satellite. And with enough satellites, your phone can calculate your position. But there's something important to understand. Your phone doesn't need to see the satellite. It only needs to receive its radio signal. High above Earth, GPS satellites orbit at an altitude of roughly 20,000 kilometers. They're moving incredibly fast, traveling around the planet in about 12 hours. And they're constantly broadcasting information. Think of each satellite as a giant radio beacon floating in space. It's essentially telling your phone, "I'm here. This is the exact time, and here's the information you need to calculate my position." But how does the satellite know the exact time? This is where things get really interesting. GPS satellites carry extremely precise atomic clocks. These clocks are incredibly accurate. They can measure time with extraordinary precision. And GPS needs this level of accuracy because radio signals travel at the speed of light. Light travels roughly 300,000 kilometers every second. That means even a tiny timing error can create a surprisingly large positioning error. An error of just 1 microsecond can correspond to roughly 300 meters of distance, so GPS needs extremely precise clocks, and that's exactly what those atomic clocks provide. Now imagine that a satellite sends a signal toward Earth. The signal travels through space and eventually reaches your phone. Your phone knows when the satellite transmitted the signal, and it can determine when the signal arrived. The difference between those two times tells your phone how long the signal was traveling. Because the signal travels at the speed of light, your phone can convert that travel time into distance. This process is called ranging. But there's a problem. Your phone doesn't have an atomic clock. Its internal clock isn't accurate enough to measure these tiny time differences perfectly. So if your phone's clock is slightly wrong, the calculated distance will also be wrong. And this is where multiple satellites become extremely important. Imagine you're standing somewhere on Earth. One satellite tells you that you're approximately 20,000 kilometers away from it. that doesn't tell you exactly where you are. It only tells you that you're somewhere on a giant sphere surrounding that satellite. Now, add a second satellite. The possibilities become smaller. Add a third satellite, and your position becomes much more precise. But GPS needs one more piece of information. It needs to correct the error in your phone's clock. That's why GPS typically uses at least 4 satellites to determine a 3-dimensional position. The 4th satellite helps solve the timing problem. So your phone is actually solving several unknowns at the same time: your latitude, your longitude, your altitude, and the error in your phone's clock. This process is based on a mathematical technique called trilateration. And there's an important distinction here. GPS doesn't primarily determine your location by measuring angles. It uses distances. Your phone calculates how far away it is from multiple satellites. Then it finds the point where those distances intersect. Let's make that easier to understand. Imagine 3 friends are standing in different locations. Each friend knows exactly where they are. They also know how far away you are from them. The first friend tells you, "You are 5 kilometers away from me." That means you must be somewhere on a giant circle around that friend. Then the second friend gives you another distance. Now the possibilities become much smaller. Finally, the third friend gives you another distance. The intersection of those measurements reveals your approximate location. GPS does essentially the same thing, except instead of 3 friends standing on the ground, it uses satellites flying through space, and instead of circles, it uses 3-dimensional spheres. Your phone calculates the distance to several satellites and finds the location that fits all of those measurements. That is how GPS can determine where you are. But now comes one of the most fascinating parts of the entire system. GPS wouldn't work correctly without Einstein. Yes, the same physics that describes time and space in the universe also helps your phone find your location. And there's an important distinction here. GPS doesn't primarily determine your location by measuring angles. It uses distances. Your phone calculates how far away it is from multiple satellites. Then it finds the point where those distances intersect. Let's make that easier to understand. Imagine 3 friends are standing in different locations. Each friend knows exactly where they are. They also know how far away you are from them. The first friend tells you, "You are 5 kilometers away from me." That means you must be somewhere on a giant circle around that friend. Then the second friend gives you another distance. Now the possibilities become much smaller. Finally, the third friend gives you another distance. The intersection of those measurements reveals your approximate location. GPS does essentially the same thing, except instead of 3 friends standing on the ground, it uses satellites flying through space, and instead of circles, it uses 3-dimensional spheres. Your phone calculates the distance to several satellites and finds the location that fits all of those measurements. That is how GPS can determine where you are. But now comes one of the most fascinating parts of the entire system. GPS wouldn't work correctly without Einstein. Yes, the same physics that describes time and space in the universe also helps your phone find your location. GPS has to account for 2 effects predicted by Einstein's theories of relativity. The first comes from special relativity. GPS satellites are moving extremely fast compared with someone standing on Earth's surface. Because of an effect called time dilation, moving clocks run slightly slower. But there's another effect. The satellites are much farther away from Earth's gravitational field than we are. According to general relativity, clocks in weaker gravity run slightly faster, so the clocks on GPS satellites experience 2 competing effects. Their speed makes them run slower, but their weaker gravitational field makes them run faster. The gravitational effect is larger. As a result, GPS satellite clocks run slightly faster than clocks on Earth's surface. The difference is incredibly small. We're talking about microseconds per day. But remember, GPS is measuring distance using the speed of light. Even a tiny error in time can create a huge error in position. Without these relativistic corrections, GPS would quickly become inaccurate by kilometers. So every time you use navigation on your phone, you're indirectly using Einstein's physics. But if GPS is so precise, why does your phone sometimes show the wrong location? Because the signal has to travel through the real world. The signal starts thousands of kilometers above Earth. Then it travels through the atmosphere. It can be reflected by buildings. It can be blocked or weakened by mountains, trees, and other obstacles. This is why GPS usually works best outdoors. Inside buildings, the signals can become much weaker. Modern smartphones also don't rely only on GPS. They can combine satellite signals with Wi-Fi networks, mobile towers, Bluetooth signals, motion sensors, and other technologies. This allows your phone to estimate your location faster and sometimes more accurately. So when you see that little blue dot on your map, it's often the result of several different technologies working together. And now, the next time you open a map and see that tiny blue dot showing exactly where you are, remember what's actually happening behind the scenes. And perhaps the most incredible part is this. Every time your phone tells you where you are, it's doing it by listening to signals that began their journey from space. So, the next time you see that little blue dot, look at it differently. Because you're not just looking at a map. You're looking at one of the most impressive technological systems ever built.